Good afternoon, Kirk. How are you doing?
I think I'm doing reasonably well. Getting all geared up to cook my world famous spaghetti sauce tonight for supper. Although probably only less than half a dozen people know about it.
Well, now I really have to make a trip out to
Yeah,
southern Ontario there, and
yeah, it'll be
since it's world
unforgettable.
famous, at least it should be seven
I
people.
say world famous because that's what it should be. It is so good. Everybody who has it just raves. It's like a whole different universe of spaghetti sauce compared to what we're
Oh,
normally used
okay.
to.
So what's the trick?
It's tough to say. There's a number of good ingredients, but I think one of the big attractions is that I melt about, I'd say, at least a quarter pound of mozzarella cheese into the sauce
Right into
once.
the sauce. Nice.
And I tang it up a little bit, just enough, with some Tabasco sauce or crushed habanero peppers or whatever. Just enough, not
I
to
know.
make it
I knew the
uncomfortable.
peppers would be a part of it,
Yeah,
but
yeah, that they gotta be.
nothing like blows off the top of the stove or anything.
Yeah,
But enough
no.
to. Okay. Oh yes. It's thanks for doing this a little bit later. I had to speak in our chapel today, so
Yeah,
that
no
happens
worries.
right after normally we do our thing, and I
Hmm.
had to do some stuff before. So
Yeah.
so thank you all for joining us. Um, so Kirk, how are you doing? What's going on in your life these days?
Well, I've been doing an awful lot of snow shoveling the last week or two. It's just unbelievable.
Do you have a
Some,
blower?
I do. I do a blower, a big one, like a 42 incher on the front of my lawn tractor. But even then, a couple days ago, it was almost 2 hours of blowing. This morning, it was maybe about an hour solid. And a lot of that was spent up near the road. My driveway is about 140 meters long. But the
That's like
snowplow,
6,000 feet.
yeah, yeah. Well, no, no, not 6,000. It's more
I'm
than a
just kidding.
football field.
Yeah,
It's more than a football field
I bet you it
in like
felt like 6,000 feet when you're in that for an hour now.
the biggest problem is the snowplow leaving a gigantic wall of snow that's high, and because he's going so fast, it's extended down my driveway. So that
So
took
do they follow it up with a front end loader or anything like that? Like
no,
when
no. I
they
live
do
in
our roads, they'll follow it with the front end loader and do the end of the
wow.
driveway. Now, I love it, but they also dump it onto our lawn, which would be okay if it wasn't for the ice and the gravel.
That's true because having had four boys, a gigantic pile of snow on the front lawn would be almost heaven as far as digging tunnels and everything goes.
Well, this
But
is hard stuff. This is
yeah,
like a lot of ice
the
and
chunks of
slush.
ice and rock and stuff and salt, not so good.
Yeah. So is the snow still coming, or is it gonna take a
Today
break?
is nice. Sun's actually shining today. There's no wind. Yesterday it was about gusting to about 50 miles an hour or 80 kilometers per hour. So the drifts were huge. It was ridiculous. But today I'm feeling pretty good.
Good, good, good. Well, so when we were figuring out what to talk about today, you said, "Hey, there's this article." So you sent me this, and I did skim through it. Like I said, it was a little bit swamped this morning, but interesting.
Yeah.
So we got these rock rockets flying around up there with the key building blocks of life.
Hmm. Yeah. There's.
They're saying it's probably widespread.
Hmm.
Now, what
Well,
was it
we
about this that got you excited? Because, like, I've always assumed that they've always said this, haven't they?
they have always said this, same old, same old. But this is maybe just a little more. What generally they might be more excited about is that they were able to actually go to the asteroid and not just
Yes.
wander around on fallen ones here on Earth that have gone through a lot of burning through the atmosphere and stuff. So they were actually able to go to one out there and bring back a sample so it wasn't damaged or altered by the atmospheric entry and the heat generated there. And what they found is a lot of amino acids, 14 out of the 20 common one used for life, 14 of them, as well as some of the as the basis that are needed for building DNA and RNA. And so part of the problem is how, like one of the things science has occupied itself with is how do we get life emerging all by itself without any help. Oh, hold it. What's this? Oh, my music application just started to fire up accidentally. I must have hit something and it was playing, playing
I can
music.
hear it. I can.
Oh, that's good. It was drowning out everything in my earphones. So, yeah, so there's this, there's basically at one point in time, for much of our human history, we kind of attributed, and different cultures would have different ways of looking at it, but there was a creator, there was some sort of a god out there, depending on what culture you're looking at, who was ultimately responsible for creating life in the world and everything else. Now, that would vary wildly depending on what culture and when in history and so forth. Now, science came along, and at first it was mostly Christians, or not just Christians, but let's say theists, who were advancing science, because one of the things we've known since, well, the oldest book in the Bible, the book of Job, talks about the laws of nature that govern the cosmos. So that provided a basis for science, for repeatability, and what are these laws, and how do they work in this world. But more recently, with the rise of a new philosophy, well, it's not a new philosophy, atheism has been around since, well, who knows when, but it was very important to be able to explain things without having to acknowledge the existence of a creator, of God. So we're looking for a natural way life could have arisen. And that's a massive problem. We have been working on it for over a century, and maybe really seriously for maybe like 75, 80 years. The Stanley Miller experiment back in, I think it was around 1954, 53, somewhere in there, trying to find a way to naturally produce amino acids. Now, you might be wondering, what are amino acids? But we'll put that on hold for a second, just to summarize what I've said thus far. So basically, science has sort of assumed its own kind of religion. It's called scientism. Not all of science, but scientism is kind of like atheism dressed up in a lab coat. So everything under scientism must be explained just through the laws of nature and the initial conditions of the universe.
So is it like a synonym to naturalist, or is there am I thinking of something else there? Like
Naturalism, yeah, materialism, all very closely related. Materialism is more like nothing exists except the material stuff in the universe here. Space-time, matter and energy, that sort of thing. That's materialism. And naturalism would be very close related. That is, everything must have a natural explanation. Not, the laws of physics, initial conditions of the universe. And scientism really kind of almost deifies science. In other words, science is our tool. It is, in fact, it's not just a tool. It's now regarded as the ultimate bastion of truth, because it is so objective and so methodical. Now, the reality is that science has been badly corrupted by what the science journal Nature describes as perverse incentives, competition for funding, and so forth. But I'd say it's also been corrupted by this allegiance to atheism. In other words, you can have a perfectly, with advances of science now, it's looking increasingly likely, In other words, the fingerprints of an intelligence behind life and behind the universe are becoming more and more obvious all the time. So we have this huge answer sitting there, and there's just a state of denial. We're just denying that intelligence was involved. Rather, we're trying to come up with a way to see how life would arise by itself. And so this asteroid, actually what they found was what they call some of the basic building blocks of life. In other words, the basic components for DNA, and I'll clarify what I'm talking about here in a minute when I say DNA and proteins. But the basic components of DNA, RNA, and proteins. And they found these basic building blocks, and you might think, wow, we found the basic building blocks of life. We're well on our way now to explaining how life arose naturally. If you think that, you would be massively mistaken. And I'll explain that in a minute or so too. So how does that sound, Sheldon, as far as kind of like a background?
Yeah, and as I'm reading here, I'm like, okay, similar stuff, including amino acids, have been detected in meteorites before, but they're after they come into Earth, so they're not perfect. Where this one, because they're getting it from the original area, it makes it a much more pure sample. I guess you can.
Yeah.
It's less likely to get the Earth's life blocks all over it. So let's dig into this. Amino acids. They're saying they got 14 of the 20 that life on Earth uses to form proteins. Now you have a little bit of background in this.
Oh yeah, I forgot to mention that. Yeah, I did a PhD in biophysics at the University of Guelph, and have since published a few papers in this area in science journals. But I focused on how do you identify or detect functional information encoded in things like DNA and proteins, and secondly, how do you quantify it? How do you measure it? So you've got to identify it, then you have to measure it, how much is there. And then third, which was the most complicated and biggest part of my PhD project, was what does this information do in terms of making a protein useful for biological life? I'm trying to state a layman's terms as much as possible. Well, because there's no point in talking about stuff if nobody understands what you're saying.
Let's talk about it this way. That you have, let's say there's 20 different colors and sizes of Lego you need to create the house.
Yeah.
They found 14 of these.
Yeah, 14 Lego pieces, let's put it that way.
Okay. Now, are those other 6 important?
It turns out that they all are. They're all important, but they're hoping that they will find, like some scientists have said, oh, we could have maybe a sort of a rudimentary type of life with maybe fewer amino acids, and then later on, because the amino acids themselves, these Lego pieces, you can sort them out into different categories. And so there are some of the scientists say, well, we only maybe need one from each category, and then we'd be on a roll. Well, the reality is, and my own research showed that no, that's not going to work. At some point, you're going to need each of the 20 on different proteins. You're going to need each one of those. So let's go back to the Lego block analogy. So just imagine that you got a package in the mail, and it was a tube. And in that tube were a bunch of Lego pieces all attached together in a long chain. And as you pulled those Lego pieces out, and remember, we're talking about 20 different kinds of pieces, so you could use the same kind multiple times in the chain, but you got this chain that's roughly 300 Lego pieces long. That's the average length of a protein. So the Lego pieces represent the amino acids, and the chain represents a protein, which is just a chain of amino acids. In this case, a chain of Lego pieces. So as you pull this chain out, what you notice is that it collapses into a stable three-dimensional structure. Well, that would be pretty impressive. But it collapses into a stable three-dimensional structure, and that structure, it'll do the same structure every time you pull it out of the tube. In other words, in
So
biological...
in the tube, they're all like separated, but
Well, no, let's assume they're all attached in one long chain inside the tube.
Okay, so okay.
And you just pull them out of the tube like this. And it doesn't stay in a long chain. It just sort of all collapses in on itself, and you get this three-dimensional structure.
Okay, so a house gets created.
Well, that would be a bit too far. Let's say an amazing... let's say you take those Lego pieces and you build a much larger component. Let's say a Lego motor for an airplane that you want to build. So that one protein won't build the house, or that one structure won't build it. But it is an important part. Or if you're thinking about cars, it all collapses into, let's say a bolt or a nut or a particular piece. And if you get a bunch of them, you can make a wiring harness. But we're getting too complicated here. Let's just keep it simple. Now, here's the thing. The shape of that three-dimensional structure will depend on the sequence of the Lego pieces inside the tube. Okay? In the same way, the shape of the three-dimensional structure that a protein will typically take depends on the sequence of the amino acids. And they're all in a chain. They're put together. Now, all the amino acids are assembled into a long chain, but the chain collapses into this three-dimensional structure. And so we're talking about Lego pieces here. The Lego pieces are in a chain. There's 300 of them, 300 total pieces, but for each link in that chain, you've only got 20 choices because there's only 20 different kinds of Lego pieces. So you pull it out, and you get this nice three-dimensional structure. You have another tube comes in the mail with a different sequence of the same Lego pieces. The same Lego pieces, all 20 of them, but they're sequenced differently. You pull that out of the tube, and it collapses to a different three-dimensional structure. Now, what you'll find is that it's not just one particular sequence that'll collapse to that structure. There could be a lot of different sequences that'll still collapse to the same structure, and you would call that subset of sequences, you'd call that a family of Lego piece sequences that collapse to the same, let's say, Lego motor or Lego bolt or whatever it is you need to build that larger thing, which the larger thing in biology would be, let's talk about humans, with humans. So humans, we have roughly 20,000 proteins. 20,000, and these proteins, about roughly 70%, maybe 75%, they have stable three-dimensional structures once they're formed, once the chain forms. Like pulling that string of Lego pieces out of the tube, and it collapses into this nice structure. So that's why they're important for life, because you are built. Let's say if I was looking at a Lego Sheldon here, Sheldon, you'd be built out of 20 different Lego pieces, all amazingly sequenced together such that they formed larger sections like the retina in your eyeball or, whatever. And then those would be assembled, those larger pieces assembled to basically build a Lego Sheldon. So you got to start with the Lego pieces. And so this discovery that they made on this asteroid called Bennu, what they're discovering here is 14 of those Lego pieces were found on this asteroid. They only need 6 others, but the assumption is that you would find them somewhere else. So
Okay,
you might
so
think...
it talks about like thousands of organic compounds and 14 of the 20 amino acids. So what are these organic compounds that we're talking about? Is that like different types of dust?
No, well, it'd be different kinds of molecules that have usually that have carbon in them. And so carbon will bond with other things and produce amino acids and other so-called organic compounds. Organic doesn't necessarily mean it came from life.
No.
So
the picture of this asteroid, like I'm not seeing a lot of trees or anything.
No.
So I'm just quite like when when I think of organic, I think of really overpriced bananas.
Yeah.
But in this case, it's just anything that might have types of, well, is the asteroid all made of organic
No.
stuff?
No, and they were pretty clear. They didn't find
there's
any.
some stuff in here that was. They got a bucket of dust off
Yeah.
the asteroid, and within this bucket of dust, they found thousands of organic compounds.
Yeah, different molecules that involve carbon is a big one, but the ones we're really interested in would be the amino acids and the nucleobases to make DNA and RNA. Now, the perception that the reader gets when they read the article is that, oh, science has made another significant advance in how life might have arisen naturally. But I want to explain that it is no. It's kind of like you found this old abandoned house, and you found this amazing book of just a written set of instructions on how to build a supersonic jet. And it was all using alphabet characters to write those instructions. And you might say, well, how did we get this set of amazing instructions on how to build a supersonic jet? And then you happen to notice in one of the rooms that there was some children's plastic alphabet characters laying on the floor. Now we have 26 characters, and let's say we found about like 18 of them. Found 18 alphabet characters laying on the floor. So you notice that, wow, we got 18 out of the 26 alphabet characters used in this book that tells you how to build, oh, let's go big here, let's go large, an interstellar spaceship, okay? So you got 18 of the 26 of the characters that are used in that book. Now, how close are you now to being able to explain how an interstellar spaceship could arise naturally? Because you found 18 alphabet characters on the floor. Well, let's say you found all 26. That your problem, the fact that you have all found 26 alphabet characters is of no help at all. Virtually no help at all in writing a book that explains how to build an interstellar spacecraft.
So you've got an unlimited supply of Scrabble sets. And all you need to do is shake it enough that it creates the dictionary.
Yeah, you could shake it, whatever, just throw it around, let the wind blow it and stuff. Now, let me get back to this problem here and using that kind of an analogy. So any sequence of amino acid, let's say you're 20 Lego pieces, any sequence at all will give you a chain. And we can call these chains proteins. But almost none of them will collapse into a stable three-dimensional structure. That's the problem. So what you have to find are just those sequences that if you put the Lego blocks together in that sequence, it'll collapse into a stable three-dimensional structure that you can then in turn use to mate with other structures to build, let's say, a frog or a human or something. So you might ask, well, how common are these sequences that give you that stable three-dimensional structure? And that's part of what I was able to do in my PhD program, was write some software that would look at massive databases of protein families. So when you think about a protein, I said we got about 20,000 of them in the human body. When you think about that, these proteins, as I mentioned earlier, the sequence of those amino acids, or the sequence of the Lego blocks forming that chain, very important, that gives you the structure. But there's a lot of slop involved, or allowed, so that you don't have to have the sequence exact. You can have it turns out there's a lot of different sequences, provided some general overall patterns are obeyed, that will give you the same three-dimensional structure, and you could call that set of sequences a protein family, consisting of all the different sequences that'll give you that same three-dimensional structure. But, as I said, there are most of the proteins, most of the sequences will not give you a stable three-dimensional structure. They'll just collapse to some random shape a blob. We call them amyloids because they would stick to other collapsed proteins and whatever. So here's the question. If if you wanted to search, if you had evolution searching for the right sequences, how big would this search have to be? So imagine space has these bubbles floating around in it, and each bubble is roughly 1 meter in diameter, in radius, or 2 meters in diameter, or let's use yards and meters are pretty close, 2 yards in diameter. A bubble in space, and you have to accidentally find, so anything in that bubble will collapse to a nice three-dimensional structure you're going to need, but you're going to need lots of them. You're going to need about 20,000 of them to build a human. So how far away would the next bubble be in space? Because you're going to have to do a random walk between the bubbles to find these other bubbles. Turns out, I got some numbers here. Where'd my numbers go? Did I write these numbers down? No, they're still sitting on the calculator here. Yes, okay. So it turns out that these islands, so let's fill the universe with proteins, okay? With amino acid sequences. We'll fill the entire universe with protein sequences, amino acid sequences. So we got a universe of proteins now, all just randomly generated, but all the ones that fold to this nice particular fold that mark one protein family is a little bubble in the whole universe that's roughly 2 yards or 2 meters in diameter. Okay, so the question is, how far would you have to search to find the next bubble? Because all these other ones are useless to biological life. They just collapse to random shapes, and you can't build anything with them. They're like Lego blocks that are they're melting, and so they take a different shape all the time, never repeatable. You can't do anything with them. Turns out you won't find another bubble in the entire universe. That's how rare these things are. You will not find another bubble in this entire universe. In fact, you would need, how many universes would you need to sort through before you found another bubble on average? On average, you would have to sort through 10 with 34 zeros after it. That's how many universes you'd have to sort through before you found, on average, another bubble.
So you're talking the odds, right? This is the odds of finding another bubble.
That's right.
Are like.
Well, you can either put it in terms of odds, but I find that people who have embraced the philosophy or the religion of scientism, they get angry when you talk. Literally, some lose it. They literally lose the composure when you start talking about odds here. So I kind of stay away from odds.
Okay.
What I want to talk about is target size. Now, target size, odds, same thing, really. How small is this target versus where we're aiming? How accurate do we have to be to hit the target, which is find a sequence that gives you a stable three-dimensional fold? On average, you're going to have to sort through 10 with 34s, or 1 with 35 zeros after it. That's how many universes, the same size as ours, that you're going to have to search through before you find even one sequence that codes for a stable three-dimensional protein. Now, I didn't make that number up. I didn't pull it out of my back pocket. That arises out of hard data, so that you can actually look at, for many protein families, 20,000 different sequences that will code for that same protein structure. 20,000, and then from that the software will look, what is the pattern that we observe in this massive array of sequences? Like, what's the probability of this amino acid working here, and what about that one? That one works too. Okay, add that. And so it does all of that work, which you'd never be able to do in a human's lifetime if you didn't have a computer. But you do all of that work from real data, and it tells you just what your target size is. It tells you how rare these stable proteins are. So
let me repeat this back, and I know I'm going to mess up here because I went through school and that's all my teachers told me. So we have 20,000 of these proteins in our body, made up of amino acids, and the amino acids have how many amino acids? 20?
There's 20 that are commonly found for biological life, and they found 14 on the asteroid.
Okay, and then each protein is made up of 300 amino acids.
On average, you'll find really short ones, you'll find
Okay,
much
that's
longer ones, but the average is 300 amino acids,
And-
more or less.
And the chances of one of these proteins occurring in the exact same way around the universe is really, really small.
Well, it's worse than that, Sheldon. It's the chance of finding any biological protein or the sequence for that. And we started with filling the universe with not amino acids but proteins. On this asteroid, they just found amino acids. You got to chain those together to form a protein. And then you can't just throw them around on the surface of an asteroid. You got to pack the entire universe full of them.
Okay.
It's full of proteins, and if you did that, you would have virtually no chance at all of producing one that will collapse into a stable three-dimensional fold. Given the real data.
So to actually get it to happen once, naturally, you would need trillions and trillions and trillions of universes.
Yeah, you'd need roughly 10 to the 35th power of universes, and each universe is not just has, asteroids with amino acids on them. No, each universe is packed full of proteins, biological and otherwise.
Okay, and then, we've lost the whole audience, so that's okay. But I want to figure this out. So, how long, let's say instead of 14, they found 20.
Yeah.
Actually,
Sure.
let's say instead of 14 of the 20, they found 20, and they had 300 of them all together. That's one protein, right?
Yeah.
Approximately.
Oh, that would make the big time news. Big time.
Okay. So, what does that protein do by itself?
Well, it'll do one of two things. It'll just collapse into, they'll all collapse, probably.
So you need more than one at a time to actually be useful.
Well, in the right environment, all chains of amino acids are likely to collapse, mostly into some random shape that is not repeatable. It'll be different every time. Or a biological protein will collapse into a stable three-dimensional structure. At least about 75% of them will. The others are called, they basically don't have a three-dimensional structure. They're intrinsically unstructured. But usually when they bind to something, then they assume a structure.
So, but how long do these things, because these are the building blocks of life.
The amino acids, yeah.
How many of them to get the most primitive life? I remember in science class talking about that one-celled organism that was like the start of life. You're at the swampy area, and it's the perfect thing for life to happen. So you need all of this to make that one cell happen, right?
You would need, now the number that, there's a lot of different papers that speculate as to what's the minimum number of protein coding genes we would need for the simplest life form. And a lot of those experiments in the past at least started with the simplest life form we could think of, which was M. genitalium. But a lot of work has been done since then. So let me just ask ChatGPT here.
Oh, yes.
How many proteins are required for a minimal life form? So it's not going to give me a nice simple answer. Yeah, M. genitalium has about 350 to 400 proteins. But they have experimented just how many could we take away? Yeah, okay, so I was going to say about 285 different proteins for the absolute simplest life form. ChatGPT gives me a bigger range here, 250 to 300, but I'm right in there. I'm right in that range.
Okay, so So I'm going to interrupt you here. I'm going to
Oh
just
yeah.
say let's do 200. Let's not 300, but or 285.
Let's
Let's
make it
just go down.
simple. Yeah.
Let's just make it simple. Round
Yeah.
number 200. That's for one cell approximately, right?
Yeah.
Okay.
That would be for the absolute simplest life form, and I'm not sure it could survive
Well, that was
without
going to
getting
be my
its.
next question. Like, not only does it need to survive, it needs to split into two. Correct? Because there's nothing to
Well,
make.
yeah, it's going to have to replicate. Yeah,
So
it's going to have to replicate.
how long does it have in the perfect situation before that one cell dies because there's nothing to eat?
Oh, yeah, I mean, you're hitting the nail on the head here, Sheldon. There are a host of problems in the origin of life. In fact, here's a choice quote I took from this article. It says this: more research is needed to understand what precisely causes life to emerge. Now, that is probably one of the largest understatements in human history, right there. I think that's towards the end of the article here. More research. I just about fell off my chair laughing when I read that. More research. More research. Yeah, okay. Good luck with that, because what the science is saying, and this is the problem, is that what the science and the data is telling us is that life is not going to happen in this universe. In fact, you don't have to just listen to me. There's Eugene Koonin is an internationally distinguished evolutionary biologist, and he's talking about what are the chances of getting not the simplest life form, but just RNA replication, which is even simpler still. What are the chances that, in his paper, it's not going to occur anywhere in the universe, in the history of the universe? It's not going to happen. His solution is to invoke an infinite number of universes,
Right.
which is what you're going to need. Well, there's another way.
But again, like, let's say you have found that second protein.
Yeah.
They
Well,
have
you'd
to
have
be
to.
close enough together. They have to be close enough
That's right.
together to actually be together,
Yeah.
and you need 285 of them for the simplest life form that we know of.
Yeah.
So not only do you have that, like you scale this sucker out, and there's just nothing. Like, you have more in the little what's the, not subscript, but what's the top number there with the zeros?
Oh, the superscript.
Like, you'd run out of zeros.
Oh yeah. What you have to start doing is you have to put superscripts on the superscripts.
Okay.
Like 10 to the 10 to the 127th power, that kind of stuff.
So this is to get potentially the simplest block of life. Then you need, what did Bennu not have that Earth did have?
Well, I mean, it's a pretty hostile environment on the surface of an asteroid.
Absolute perfect situation for that one cell to live long enough to figure out how to replicate itself before it died. Because once it died, you need to start over.
Absolutely. I mean, you got so close. You had a life form here, but and let's go with one cell where they can simply split in half. But you need to reproduce the DNA in that organism so that when you split in half, both of them have the instructions on how to keep doing what they're doing. Plus, they need some sort of nutrients. Now, you could, you can have bacteria that will feed off stuff that, let's say, crude oil, for example.
Okay, but like, where'd that come from?
Well, yeah. I mean, that's a problem too. We haven't actually figured out how we got so much crude oil on this planet. It's a big mystery, and I've read a lot of different speculations on that.
But that organism would have to be attached to the crude oil.
It would have to. There's a lot of
to be able to survive.
Sheldon. You're talking about winning a massively improbable lottery just to get one stable three-dimensional protein. But then to have another one occur somewhere in the universe, and not just somewhere in the universe, it has to be like right beside it in order so it can assemble and to build something bigger with it. Like these Lego chains, the Lego pieces build the Lego chains collapse into a stable three-dimensional thing, and now you got to build the rest of the whatever it is you're building. And so it all has to happen at the same time in the history of the universe, on the same planet and the same spot in the planet. And there has to be all this fortuitous stuff going on. When you actually dive into it, it becomes so
And it can't die. And it cannot die.
it has to
And
survive.
neither can any of the things that are replicating, because
Well, you see,
you need to have
there you
enough of those replicating to actually
Yeah.
produce anything beyond that simple organism.
Yeah, it has to build its own amino acids so that it can build its own proteins. Like once you got up and running, you're gonna have to get more amino acids to build more of these proteins so you can split in two and continue on replicating like that. Sheldon, I will have to say that the theory, if you want to grace it with the title of theory, the theory that life arose naturally is by far the wildest idea, wildestly fantastic idea humanity has ever come up with. Fairies would be much more easier to genetically engineer. A piece of cake in comparison to the origin of life. Say fairies that fly around, or unicorns, dragons. I mean, I'd imagine with genetic engineering, and we could build something like a dragon. Maybe take the genetics of the bombardier beetle that fires two chemicals out his backside and they ignite and make a little explosion. We could actually genetically engineer a dragon with enough work and funds. So we can build all these fairy tale stuff. But how to build the first life form? We've had thousands of scientists working on this for over 100 years. And we are, and in fact, in one sense, this article shows the pathetic state that science is at when it comes to coming up with a natural explanation for the origin of life. We're still stuck with how do we get the initial building blocks? Forget about proteins and RNA and how we're going to have that all happen in the same place. We just want to get the building blocks. It's like you find this magnificent book of instruction on how to build an interstellar spacecraft, but you're at the stage where you're still looking to figure out how the alphabet's made. How do you get these alphabet characters so that book can be written?
I found this interesting because they sort of moved the needle here. They found sodium carbonate compounds referred to as soda ash. So maybe that's because of all the people doing those Mentos in a Coke bottle experiments, blowing those up into space. I don't know where that's coming from, but so okay, this might exist on Saturn's moon and a dwarf planet. They said here, where did I see it? While the samples from Bennu have already yielded intriguing results, more researchers need to understand what precisely causes life to emerge on one planet or moon than others. What did Bennu not have that Earth did have? Well, one, they didn't have the other six
amino acids.
Mm-hmm. What it had all the stuff but didn't make life.
Well, not all the stuff.
It didn't have all the stuff, but like that's what I'm saying.
But if it did, it still would be no closer.
Yeah,
still be no closer to making life.
Okay, and they didn't say like is this? So it's showing sodium carbonate. So are these? Like, are we talking? These are the amino acids. Are there amino acids in this? Is that what they're saying?
Well, I don't know the chemical structure of sodium carbonate, but I think it's just a standard molecular compound of sodium and carbon. I don't know what that is here. What is the chemical structure? Let me. me see here. Sodium, carbon, and oxygen.
Okay.
So it's called soda ash, in everyday language, or washing soda. Use it for water softening.
Yeah.
But this is really, let's say, forget about the book telling you how to build an interstellar spacecraft. Let's say you wanted to build one and you knew that you're going to need some titanium, you're going to need some silicon dioxide, and you look around and you see sand on the beach and you say, oh, there's some silicon dioxide. You start mining and digging around the dirt, there's some titanium. We have found the building blocks of interstellar spacecraft. That's pretty much where we are at here. Pretty much where we are at. There's a missing ingredient here. So remember that I told you that the chance of finding any combination of amino acids useful for biological life is so small you'd have to sort your way through 35 universes full of proteins to find one that would actually give you a stable three-dimensional structure. Well, what do you do when you have a serious problem like that? Well, you do the same thing when you want to, let's say, open the vault at the bank. You don't go in the bank, let's say you're a new employee, you don't go just to the vault, boss says open the vault, so you just don't go in there and start randomly trying numbers. You're going to be there, that's going to be your career. Instead, what you're going to look at is at the boss, and you're going to say, well, I need some information. What is the proper combination? In other words, when we see effects, and there could be anything in this world, you see a car, plane, laptop, computer, these are all examples of intelligent design. And last week we punched in the question, is a laptop computer an example of intelligent design? And ChatGPT says yes, of course. And so when you ask what are the characteristics, well, there's 4 things. But you see, what the problem is for information is that information actually reduces the uncertainty. And we've already seen the uncertainty of finding one of these proteins useful for biological life. It's huge. So if you want to reduce that, you're going to need information, and information actually reduces the uncertainty down to essentially 0 if you're lucky. And that comes from, to produce massive quantities of information, there is only one thing that science has discovered that will produce significant quantities of useful information. Just one. It's the only thing that's repeatable, verifiable, observable, and that's intelligence. That's it. You can accidentally produce very low levels of information, like a 2-letter word accidentally dumping some stuff on the floor. But there is a threshold. You got to start looking at what is the target size, what's the probability of getting that, and you see, or how uncertain am I if I generate a sequence of Lego characters that it's going to collapse into a stable, useful 3-dimensional structure? How uncertain am I? If you have no information at all, you're going to be very uncertain. For proteins, you're going to have to sort through randomly 35 universe fulls of proteins. But if you have information, if you actually understand how the structure is determined by the sequence, then you don't have to start doing this search anymore. Intelligence can actually build artificial proteins, and we've already started to do that. Human intelligence. Now, granted, we have plagiarized a bit. We're basically reverse engineering proteins to see how they fold. But, we're able to take that information and build a new protein, a novel, very simple protein. But what's critical there is you have to have a mind. You have to have an intelligence. Instead of randomly sorting through 35 universes. So this asteroid does absolutely, it's almost discouraging to say after a century, we're still searching for how can we get the basic building blocks of life. I'm prepared to grant you all the basic building blocks of life. Let's just grant that. Let's just give it as a gift. That would be the easy problem, and they've been working since the Stanley Miller experiment, 53 or 54. Stanley Miller experiment, just to find out how do we get these amino acids. And so we can't, we have all different things. And now there's a problem here. When you get amino acids, biological life, you see these amino acids tend to have a mirror image of themselves. and it's only one type of mirror image works for biological life. Let's call it the left-hand image, okay? And what they found on this asteroid is you got both. So actually, that's a serious problem. You cannot assemble just a mixture of both left and right-handed amino acids and hope to get any protein that's useful for life. So that's actually what they found there, and they mentioned that, the chirility. Oh, no, I looked at the actual paper. That's where it was telling me about that.
They forgot to mention that in the article.
Yeah, the
Okay.
chirility.
So now I have another question. Let's say there's intelligence. The universe has intelligence. We'll say the universe has intelligence. Doesn't it also need a reason?
Well, that's a very good question. Like, you don't just
Because you can be the smartest person in the world, but if you have no motivation, you're not going to
no
do
reason,
anything.
no motivation, no reason, no goal. Like, what's the point? That's actually very interesting, Sheldon, because what they have discovered as well is that the universe appears to be incredibly fine-tuned, such that it is able to support life. So there does seem to be, first of all, something behind the scenes, let's say cooking the books, so to speak, massaging the numbers, so that we do get a habitable universe. But that in turn points that there is a reason for the existence of the universe. It's to support life. Okay, so there is a reason there, but a reason requires a mind again, so you can't just intelligently produce a universe capable of supporting life. It's not just that, it also has a reason for doing such. And once you see that the universe appears to be designed for the purpose, underscore the word purpose, of supporting life, then it should not be surprising if that same intelligence has been involved in the universe to properly sequence and code these basic building blocks to support life, in the same way that when you read a book, there has been an intelligent mind behind there properly sequencing the alphabet characters for whatever purpose the writer of the book has in mind, whether it's poetry, fiction, information, whatever.
And then it needs capability.
The capability to pull it off, yeah.
It would also, it could be intelligent, but it would also need to have the amount of power to create something out of nothing.
Yep. In fact, that's logic says it had to have that ability. Whatever it was that produced space-time, matter, and energy cannot itself be composed of those things or dependent upon those things. So it has to be non-physical. It has to be what we might call nothing, as far as no matter, no space, no time, no energy. It just thinks this into existence.
So what is now needed for science to be able to prove that life could have been created on some other planet? Like, life had to exist because all they're saying is it could have happened somewhere else first, right?
Yeah, in fact, that's where they...
Even if it's like, okay, yeah, it happened on Earth, all those building blocks had to come from somewhere else.
Yeah.
In the perfect situation to have it happen. Because it had assumed the Big Bang. Either everything has these building blocks in it, or Earth is special, because they didn't find any on the moon, did they? I'm assuming they looked.
Yeah, I think we would have heard about it if they found amino acids on the moon, and that's pretty close to Earth. You would expect some sort of pollution wafting off in the solar wind. But yeah,
Like, I'm just trying to figure out, like, at what point do we say, you know what? I don't think we're going to find it.
Well, you see, it's not what we don't know now. It's what we do know about how rare these stable three-dimensional sequences are. It's what we do know that tells us there's not a chance we will find life anywhere in the universe unless there is a mind behind this. And if there's a mind behind it, then we could easily find life all over this universe. So one of the points that I like to make is that if we discovered alien life somewhere else, that would virtually guarantee it would make it not prove, but it'd be very close to it, that there is a mind behind the universe. Because you don't, let's say you start winning the lottery once and then you win it the next week, the Lotteries Commission would start maybe investigating you if they started finding you frequently winning the lottery, way too frequently. Exactly the same thing here. You start finding life on other planets. When you know, the science says that these are so rare they will never occur in the entire universe, a stable three-dimensional folding protein.
But does science actually admit that?
Science is okay. When they use science says this, and
I'm just thinking the people that are looking for this, do they realize, like, are they in denial? Are we wrong? Like, is Kirk potentially wrong in your work?
It's not me. I mean, it's the data that's saying this. But some scientists are aware, like Eugene Koonin. He's aware that the probability that this could all cobble together by itself is so vanishingly small, you're going to need an infinite number of universes. But he interprets that as, therefore, there are an infinite number of universes. Okay. Not just possible, there is.
There has to be.
Yeah, and so let's say then it would never happen. And the other person says, well, wait a sec, we don't need an infinite number of unseen entities here to explain life. All we need is a superintelligence that already understands how these bonds occur and how the sequence will affect the structure. And with that in mind, codes the proteins, various biological proteins, into the DNA of whatever organism it's designing. That's the way we do it in the lab when we're fooling around with genetic engineering or when we're trying to build an artificial simple protein.
Okay,
we don't just
so it's pretty much impossible for it to have happened naturally.
Yeah.
Let's give them the point blah 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 percent chance.
Well, it reaches a point where you have to say it's not possible in science. Let's say 10 to the minus 50th power. When you get to little numbers like that, no, it's not going to happen.
Okay, but let's just grant that there is this remote possibility because of all these infinite universes. Mm-hmm. What created those?
Oh, well, that's another problem. Exactly, because that multiverse, so to speak, has to have a beginning. And it's not just because I said so. It's because of the nature of a countable infinite set of universes that are all spawning each other. You work backwards in time. You cannot, the nature of a countable infinity is that you cannot make any progress towards whatever universe we're in now. There's always an infinite number that still have to take place before you get to this one here. We're here. Therefore, we know that even if you did have a multiverse out there somewhere, that this chain of universes that produce more chains of universes does converge to an initial mother of all universes. Now, Paul Davies, a theoretical physicist, says, yeah, we have to admit that, but it pushes these so far back we don't have to worry about it anymore. But as a philosopher, I'm saying, wait a sec, we do have to worry about it because you've not answered anything here. You've just pushed the problem back, let's say 5 trillion universes. You just pushed the problem back. What does create nature in the beginning? And nature, in this case, would be the entire multiverse.
So you have all this energy, and we looked at what the amount of energy would have needed to be at the start of the Big Bang. So all of that needs to all happen perfectly. And they say the universe is how many billion years old?
just change from time to time. Let's say 12.5 billion, 13 billion.
Okay, so we're not even
somewhere
in
there.
trillions here.
No. 12.5
They know it
billion.
has a beginning.
Yeah, we do know that.
They admit it has a beginning. Yeah. Okay, so how much money has the world spent trying to prove a negative?
Well, I personally, on one side of me, I say if you can find, I think it is a good thing to see if there's a natural explanation. But there reaches a point in your research that you begin to find out enough to see that, as any forensic investigation will tell you, that this was not just, let's say, death by natural means. Let's say we're talking forensic science here. There was a human agent involved, or an intelligent agent in the case of life in the universe. That reaches that point. We have long passed that point. And when science continues to beat its head against the wall, when all the data and the fingerprints of an intelligent mind are all over the genomes of life in terms of digital information encoding all these protein coding genes, there reaches a point where it's just complete denial. It's just, like the emperor has no clothes, but the emperor still insists he's wearing something. One more thing I wanted to note here in this article, this is something to note in all these articles, is the use of lack of data words. This is when, these are words my PhD supervisor, wouldn't let me use in any paper I submitted to a journal. The first one was suggests. I used that once in my first paper. He said, suggests. What do you mean suggests? Do you have the data to support that? I said, no, but I mean, it does suggest, this and that. He says, take that out. This is science. We work with, if you don't have the data to back that up, then you have to not use the word suggests. But they use the word suggest twice. There's another phrase, may have. Now, I may be a little off.
This is in the article.
These are from the article.
Is this in the paper as well, or is this just...
No, I haven't read I've just read the abstract for the paper.
Okay.
At this point, but the word suggest occurs twice, may have occurs 4 times. Here's another one, is thought to have, that occurs once. Bolster the theory, now that's an interesting term, bolster. Likely is a lack of data word. So these are words that you use in science when you don't have the data to support what you're saying. So you say, well, it's likely this, or it might have been that. That's nice. You might use that in forensic science but you got to have a test to somehow, it's got to be verifiable or falsifiable. And in every way we test this, it continues to falsify the idea that you can get from these amino acids on this asteroid, or even trillions of asteroids crashing into the Earth, pounding the Earth full of amino acids and nucleobases, that you will ever get anything that's useful for life. That any kind of stable three-dimensional protein out of stringing these random amino acids together. And a massive problem, which most people wouldn't notice, is that these were racemic. That is, you had both left and right-hand versions in roughly equal quantities on this asteroid.
Okay, so I'll it's time to shut her down here, but I have one more question. So, and I know that it wasn't really scientists that wrote this article. This is NBC News. It was a reporter that might have interviewed them, but the researchers did not find any evidence of life itself. Rather, their results bolster the theory that asteroids that crashed into Earth when it was young may have delivered the necessary ingredients for life to take hold. Findings could also mean that the life forms on other planets and moons could be higher than scientists previously thought. The mission is already rewriting the textbook on what we understand about the ingredients thought to be necessary for the emergence of life in our solar system. I don't understand how they can say that when we already know, or are they just saying what we understand about how the ingredients got here? Is that what they're saying it's rewriting?
I think what they're saying is that the idea that the building blocks of life came from space rather than were constructed here on Earth, we have more reason now. So when our theories, when we're writing textbooks on how life might have accidentally come here, our theories, we're going to put more weight on it came from space.
But I don't understand how this actually helps that, because at like give I'll give the Big Bang Theory. Okay, let's say that's how it happened.
Hmm.
Why didn't Earth already have those building blocks? But
Well,
then
okay,
and
that's
then wind blew them together or something like that. Like, why does it have to come from external places to hit that perfect swamp?
well. These are more. It goes to how do we get the elements like iron and hydrogen and all these elements to begin with. And then, first of all, in a big bang, you've got a lot of heat, got a period of inflation, and then slowly, but you got you got electrons and stuff being produced, and then maybe some simple molecules or simple elements like hydrogen, for example. Hydrogen is the simplest one. And then you got star formation, and these stars, as they burn, they can produce heavier elements, according to theory. And then they explode, supernova, they blow themselves all over the universe, all these heavier elements, and then they gradually reaccrete onto other stars and planets and so forth. And it's a narrative, it's a story, okay? It's like a science fiction.
But then you got out of all of that, you you have other planets forming.
Hmm.
You have asteroids that are supposedly pulling like how these amino acids get on the asteroid, right?
Yeah, well, they're thinking there was another world or another planet or somewhere, and
Why did
it got
but
nailed.
how did it get it? How did it get
Oh
there?
yeah, well, it just goes on, Sheldon. Like when you start, the more you learn about proteins and protein structure, they're more wildly implausible. And I'm being generous here when I say wildly implausible. The more absurd it becomes to think you can get stable three-dimensional proteins through any kind of an unguided natural process. It is so beyond plausible. We have crossed the line probably 10 years ago where it becomes painfully obvious that the fingerprints of a mind are all over the genome's life in the form of information digitally encoded into DNA. And DNA it's digitally because there's only four nucleotides in DNA, so you got to arrange these into groups of three called codons, and then for these groups of three you can arrange them in the right sequence that'll eventually code for a protein that will actually fold into three-dimensional structure repeatedly. So the information, when you get above a certain threshold of information and any effect, you know there's a mind behind it. And the science is repeatedly, systematically, inexorably having this forced into its face, but many people who are totally committed to scientism have crossed the point of credibility now. I'd say Eugene Koonin is ahead of the game, at least acknowledging it's not going to occur in the universe, therefore we need an infinite number of them. But even then it becomes absurd to postulate an infinite number of unseen entities in order to avoid, don't want to look over there, avoid the idea of a mind creating information, which encodes all this into the DNA. That is so patently obvious now that you have to know that this isn't a matter of science anymore. It is a matter of what people want to believe.
It also gets into ammonia. Now, interestingly, like in my understanding of ammonia, having a dog, doesn't ammonia kill stuff?
Well, it's got components that are useful for biological life, and biological life produces ammonia. But yeah, it's too much of that in your toast. So
like about 100 times more than the natural levels of ammonia that you find in soils on Earth. Would that be enough to kill proteins?
basically, what you're seeing in this article is what I might call clutching at straws. A person has just fallen out of an airplane at 35,000 feet, along with a bunch of luggage and stuff, and you're frantically trying to grab stuff to build yourself an airplane or a parachute before you hit the ground. That's the kind of clutching at straws that's going on here. There's nothing wrong with the kind of research that says, can we see this kind of stuff occur naturally? That I endorse. It's a part of our curiosity. But the problem is that life requires information encoded into the DNA. That's the problem. So these steps here we're seeing on this asteroid, that's fine. There's nothing wrong with that. I endorse it. I support that. Looking for the components, the building blocks of life. It's part of our curiosity and search. But where we hit the wall is explaining the information encoded in the genomes of life. Life does require information in order to know what sequences of those Lego blocks or what sequences of amino acids will give us stable three-dimensional structures in globular proteins. We need to know that in order to build a body, build a human or a frog or a fish or whatever, even build a virus.
Yeah. Okay. So, but we now know, and I'll close with this. We now know from Bennu that the raw ingredients of life were combining in really interesting and complex ways on Bennu's parent body. We have discovered that next step on a pathway to life.
I would say, okay, blow the whistle at that last sentence. We have discovered that. I might blow the whistle halfway through that sentence. The next step on the pathway to life? No. Until they figure out how you can get huge quantities of functional information encoded digitally into DNA, you haven't even started. You're still looking at titanium and iron and silicon dioxide in your quest to build an interstellar spacecraft. Yes, natural ingredients are here to build interstellar spacecrafts, maybe, if such a thing is possible physically. But don't get me excited by saying we found a titanium deposit here on Earth. Therefore, we have discovered that next step on a pathway to interstellar spacecraft. It's about as impressive or not impressive.
Okay, well, now that you've picked this article apart and dashed the hopes of many people, we have these conversations because we believe in an intelligent designer who actually had a purpose for creating this universe. And the big difference is you just have to believe that there is something beyond the natural. Because if you believe there's something beyond the natural that created nature, it makes sense.
Yeah. Oh, yeah. Logically, you have to concede. Logic dictates there is something not natural or supernatural or beyond the natural in order to be able to bring nature into existence. It has to be independent of the natural world. And we know nature had a beginning. So both from science and mathematics to the nature of countable infinite sets and what it takes to get through them one at a time or not get through them.
The hard part, though, is if you're willing to grant there's a supernatural being, it opens a lot of questions.
Oh, huge. But it's a major step forward.
It's a major step forward.
Yeah.
But the reason people don't want to believe it is because
bang on. Yeah.
It's not a science question at that point.
That's right.
It's a spiritual question at that point.
Yeah. Very good point. Absolutely. There is a psychological reason or a spiritual reason why people are killing themselves, figuratively speaking, like just trying to find some natural explanation for nature and for life. And I think you've nailed it, Sheldon.
So those of you who are watching, leave a comment. Let us know where we're wrong. I'm sure we're wrong somewhere. So just let us know where we're wrong. Remember, this is what Kirk's PhD was in. And so, let us know what we're missing. And then we'd love to have that conversation with you. And leave a comment, hit the bell, subscribe, do all that, and we'll see you next week probably.
No, not next week. I'm gone. I forgot to mention that.
You're off. Okay, so whenever you're back, we'll figure it out.
Yeah, the week after.
And go to kirkdurston.com. He's got lots of good content on there. And subscribe to his newsletter, all that stuff.
Sure.
We'll talk to you later.
Bye for now.
Bye-bye.